Let's think about some of the recurrences we've seen so far. The first example was our recursive attempt at solving for the Fibonacci numbers. And there we found that we had t of n equal to a constant plus t of n minus 1 plus t of n minus 2. And what that ended up working out to, we didn't really prove this, but it ended up working out to an exponential time algorithm. It was roughly phi to the n, phi being the golden ratio. The next example is the mult function. We tried to multiply two n-bit integers. We ended up having t of n equal to O of n plus 4 t of n over 2. That was because we had to multiply our divide and conquer strategy. We had to multiply all the halves of the numbers together. That required 4 multiplications. And we concluded, although we didn't actually prove why this is true, that this gives a running time on the order of n squared. Finally, we also saw the fast mult version, which used a trick from Gauss, which managed to reduce the number of multiplications on every recursive call of the algorithm to 3. We ended up getting a recurrence of the form t of n equals O of n plus 3 t of n over 2. And of course, that led to a running time of n to the log base 2 of 3, which was faster than n squared. The question is, where did we get these? We were able to conclude from these recurrence relations, right, from the dark blue, we were able to get this, what we have written here in purple, which is the actual running time as just a function of n. The question is, how do we conclude that? We didn't really give you the tools to conclude that. We just stated those in those lectures. So today we're going to spend some time trying to understand how to actually achieve, or how to conclude those running times from these recurrence relations. So there are lots of useful facts for understanding how to solve recurrences, and one of the things we're going to start with is geometric series. So just as an example, here's a geometric series: 1 plus 1/2 plus 1/4 plus 1 over 2 to the 3 plus plus 1 over 2 to the n. Now, if you add 1 plus 1/2 plus 1/4 plus 1/8 plus 16th, so it turns out that this is actually, well, this actually ends up equaling, I think, 2 minus 1 over 2 to the n, which actually equals just O of 1, right? Also, similarly, let's say I use 1 plus 3 squared plus 3 cubed plus 3 to the n. It turns out in this case, this thing equals, it's on the order of 3 to the n. So the key thing here is that if you have any constant alpha, for any constant alpha greater than 0, what does the sum from I equals 0 to k of alpha to the I, which equals 1 plus alpha squared plus plus alpha to the k. What does this equal? Well, it turns out that if alpha is less than 1, then the first term dominates, like we saw above. The first term dominates, and that means that this whole thing is on the order of 1. And if alpha actually equals 1, well, if it equals 1, this is easy, right? This is just equal to k plus 1, which is, of course, on the order of k, right? And if alpha is greater than 1, then it turns out that the last term dominates, and this thing is on the order of alpha to the k. And if you want, we can even call this a lemma. I'm not going to prove it for you here, but it's pretty straightforward to prove this lemma. Now let's consider solving a recurrence by hand. We're going to do it the hard way. We're actually going to see an easier tool soon that'll make this a lot easier. But let's try to solve this one by hand. This is the recurrence relation we got for the mult, the not fast version, but the slower version of mult, where t of n equals 4 times t of n over 2 plus O of n. Let's see how we could possibly solve this thing by hand. Okay, to solve this thing by hand, let's observe a couple of things. Remember, what does this O of n mean? The O of n means that we can upper bound whatever this object is, we can upper bound it by some constant times n, right? So if we want to expand this thing, so to expand, we can write t of n is actually less than or equal to some c times n plus 4 times t of n over 2, right, for some c bigger than 0. right? That's what it means for something to be O of n. Whatever this term is right here, we can say that it's just an upper bounded by some constant times n. All right, let's keep expanding here. We can write that this is less than or equal to c times n, and now we're going to replace t of n over 2 using the exact same inequality. We have this as plus 4 times, okay, now let's be careful. This is c times n over 2, y over 2, because remember now the input here is n over 2, not n, okay, plus 4 times t of n over 2 squared, right? Because we now have another divided by 2 in there. Okay, let's keep expanding and organize some of our terms. I'm going to write this as Cn plus 2Cn. That was from the 4 and the divided by 2. Okay, plus 4 squared. And now I'm going to expand this out further. This is now Cn over 2 squared plus 4t times n over 2 cubed, right? We get another factor of a half there. If we organize this a little bit, we can see that this is Cn times 1 plus 4 over 2 plus 4 over 2 squared, right? Plus 4 cubed t times n over 2 cubed, right? Just organizing there. And you kind of see where this is going, right? If we continue to unroll this, let's say I times, I can get to the point where I have c times n plus 1 plus 4 over 2 plus 4 over 2 squared up to plus 4 over 2 to the I minus 1, right? Plus 4 to the I times t of n over 2 to the I, right? That's if I were to unroll this to the an I many times. Okay, so now we have this recurrence, which is, we can expand out up to I steps. We can kind of go I steps deep into this recurrence. The question is, when do we stop? When can we stop? Of course, to make this stop, to get to the kind of bottom of the recurrence, we need this term in here, right? N over 2 to the I to get down to a constant, let's say 1, right? So when is it the case that, recursion stops when n over 2 to the I is, let's say, 1, which implies that I has to equal log base 2 of n, right? That's when we get to the end of this recurrence. So what we want to do here is plug in the case when I is equal to log base 2 of n. So of course we can continue this calculation and write that this whole thing is less than or equal to c times n 1 plus 4 over 2 plus 4 over 2 squared plus plus 4 over 2 to the I minus 1. Okay, and, oh, I meant to write log base 2 n minus 1, right? Plus 4 to the log base 2 n times t of 1. Of course, t of 1 is just going to be 1, right? That's going to be a constant. We'll just call it O of 1. Okay, so let's finish this off. So notice that 4 over 2 is bigger than 1. It's 2. So this term right here is, in this sum right here, the dominant term is the last one, right? When you have a geometric series where the base is larger than 1, then the last term is the leading one. So what we have here is something which is equal to O of n, right? That's this term right here. C times n is O of n, times, again, the last term dominates, so it's O of 2 to the log base 2n. I'm going to get rid of this minus 1 because it doesn't matter. It just adds a multiplicative constant on the outside, right? So that's that first term, right? Plus second term. Well, what's 4 to the log base 2 of n? Turns out you can write that as, 2 to the 2 log base 2n times O of 1. T of 1 is O of 1, right? And of course, this thing right here is just 2, is just n to the 2, right? You can just pull down the log base 2 of n and just leave n squared there, right? So the whole thing equals O of n squared, right? And that, I get O of n squared because this term, 2 to the log base 2 of n, that's just n. So we have O of n times O of n plus this n squared term times O of 1. So it's plus O of n squared equals O of n squared, right? So the final computation is on the order of n squared. So we just did a somewhat tedious calculation to show that when you have a recurrence of the form t of n equals 4 times t of n over 2 plus O of n, that you can conclude that the actual running time of the algorithm is t of n equals on the order of n squared. And that was useful. It took us a long time to do that. There was a lot of algebraic computation there. We had to look at some geometric series. We're going to see a faster way to do that soon. But before we do that, let's just consider the faster version of the multiplication algorithm. Remember that we had a multiplication algorithm, fastmult, that required only 3 multiplications, not 4. And let's just consider how we get the faster rate and where that comes from. So let's just go through this calculation as well. Okay, so now I've gone through the same sequence of steps that we went through with the regular mult. Now we're working on fastmult. We have almost the same expression except for this 3. Let's see how that 3 makes a difference in this calculation. Like we did before, we just convert this to Cn for some C because this is just this O of n term, right? This remains the same. And now let's start expanding out this recursion. This t of n, 3 times t of n over 2 becomes 3 times Cn over 2, right? That takes, I'm basically plugging in this expression, or the inequality for this expression here for t of n over 2. I'm just expanding out further. And now I get 3 times, I think there's a mistake here. This should be n over 2 squared right here, right? And if we continue to dive in, right, I can organize these terms. I have a Cn here, and I have a 3 times Cn over 2 here, which becomes, like, I'm going to just organize all these Cn terms into 1 plus 3 halves. I'm just factoring out the Cn. And you'll notice that I have a 3 squared times t of n over 2 squared in the argument to this t. And if I keep unrolling the recursion as I'm doing, if I just go through the exact same process and I repeat it I times, you'll end up getting Cn times this geometric series with 3 half as the base, right? This geometric series, plus a term which is 3 to the I times t of n over 2 to the I. Okay, and again, what I should I plug in here? What I want is to get this thing down to be 1, right? I can just assume that n is a power of 2. And what I can plug in there is I is equal to log base 2n. So I just plug in I is equal to log base 2n, and this is the expression that I'm left with. Okay, how do we finish this off? We notice that we have we have an O of n term here, right? From this Cn, and this geometric series right here, the last term is the dominant one because the base is 3 halves. 3 halves is bigger than 1, so this is the term that we care about. Therefore, this thing right here is O of 3 halves to the log base 2 n. Okay, plus 3 to the log base 2 n times O of 1. Okay? Now, to finish this off, you'll notice that I can make this, I can actually write this thing right here as O of 3 to the log base 2 n over 2 to the log base 2 n, right? But log base 2n, of course, this is just n, right? but actually it actually gets canceled with this. I have an n up here, and I have an n down here, and I can cancel those. So this is going to cancel with this whole term right here, and I don't end up with that term. So what I'm left with is two terms that are actually the same. I have this whole thing is equal to O of 3 to the log base 2 n. And it turns out, if you remember how we manipulated logs, you can actually simplify this even further to equal to O of n to the log base 2 of 3. And we did that in an earlier lecture, how to manipulate logs to get into this form. It's n to a constant. And this, of course, is where we got that expression, n to the 1.59. 1.59 is the log base 2 of 3, roughly speaking.